Next, I'd like to discuss an aspect of special relativity that ties in with the Michelson-Morley experiment, that aspect being time dilation. Now, recall from the Michelson-Morley experiment that Michelson and Morley measured the speed of light in the east-west direction to be essentially the same as the speed of light in the north-south direction, in spite of the fact that we know that the Earth is traveling to the east with a speed of about 18 miles per second, or 30 kilometers per second, which is a sizable speed, small compared to the speed of light, but nevertheless very significant. They were able to detect no motion of the Earth through space. Einstein in 1905, at age 26, makes two very important postulates that cleared up that matter along with a lot of others that were troublesome at the time. Einstein made two assumptions. He assumed, one, that the laws of physics are the same no matter how fast the observer travels, as long as the observer moves along at constant speed. And the second postulate was that the speed of light is the same for all observers, independent of the motion of the observer and independent of the motion of the source. With those two postulates, then, we can determine a number of things about the way nature is, in particular about how clocks behave, moving clocks compared to clocks at rest, for example. Suppose I do a thought experiment in which I have a clock. That clock consists of a tube with a mirror at either end and a light beam bouncing back and forth between the two mirrors, up, down, up, down. It's kind of like a pendulum clock that swings back and forth. Tick, tock, tick, tock. So if the light beam goes up, tick, tock, we have a light clock instead of a pendulum clock. This is simpler to discuss, but it turns out that the pendulum clock will work the same way, although we're going to focus on the light clock. In fact, I want to have two light clocks. I want to have one at rest, and I want to have an identical clock that's going to be moving at a constant speed with respect to the first light clock. So this clock will continue moving on at a constant speed and just keep on going. My own arm will only reach out so far, so I have to stop it. But we just imagine that the moving clock is just drifting by at constant speed. So now I want to demonstrate with a simulated light clock that's at rest. And I'll mount that on this stand here. There's a clock at rest, and we can imagine that it's ticking, tick-tock, as the light beam goes up and down. And I have an identical clock that when the identical clock is at rest with respect to the first clock, the two light beams will be synchronized together, tick-tock, tick-tock, tick-tock. But now let's watch what happens when the clock that's capable of moving with respect to this, that is, moving with respect to our laboratory frame. This is fixed in our laboratory frame. This clock will be in motion. Let's consider what happens when this clock is set into motion. To do that, I want to refer to the chalkboard here. This is a diagram of the clock at rest, and the light beam in this clock is going up and down, tick-tock, tick-tock. Here's the clock in motion. The light beam starts here. The clock moves along, and so as the light beam goes up and down in this moving clock, let's see what happens to the light beam. The light beam is going to go straight up the tube, but the tube moves to here, and then to here, and then to here, and back down to here. Once again, the light beam in this clock is going to go straight up the tube, but the tube is moving, so the light beam is going to go to here, at a constant speed, of course, and back down to here. So in the movable clock, the clock that we're going to set into motion, the light beam is going to go up the tube like that and down the tube, following a path that would be a straight line up and a straight line down, but that line would be different than the line in the clock at rest. Let me draw that path on the chalkboard. First, for the clock at rest, the light beam is going to start at the bottom, go up to the top, and come back down again in that fashion. So the light beam is going to go up and then come back down. Tick, tock. When that identical clock is set into motion, that light beam is still going to be confined within the tube, but the light beam is now going to be traveling as we observe it. As we observe the clock to be moving, that light beam is now going to be traveling from here up to here, and then back down again in that fashion. So the light beam then is going to follow this diagonal line as the clock moves along. Let me see if I can coordinate myself so that I can actually take this piece of chalk and follow up that light beam. As the light beam goes straight up the clock, as observed from the clock, someone traveling along with the clock, they would see the light beam go straight up and down. But as we watch the clock move along, that light beam is going to go up that line and then keep going up the line as the clock gets to here. And then that light beam is going to come down the clock and back down to here. Whoops. As the light beam comes back down to the bottom. So the important thing to note about this is that the clock is moving along at constant speed all the time. I've kind of messed up the diagram here a little bit. But the speed of the clock is the same at each point along the way. This v is the velocity vector for the clock. Clock moves along at constant speed. The light beam, as we observe it, always stays within the tube of the clock, but follows this kind of a path. So, since for the clock at rest, the light signal has this shorter distance to travel, straight up and straight down, compared to the longer distance when the clock is in motion. And since the speed of light is the same here as it is here, the time it takes for the light signal to go from the bottom to the top and back down to the bottom will be greater than the time it takes when the clock is at rest for that same light signal, or for an equivalent light signal to go from the bottom to the top and back down to the bottom again. So, since the speed of light is the same, and that's the key to this whole discussion, the speed of light is the same here for the moving clock as it is here for the clock at rest. We observe the path length longer here than it is here. And therefore, the time it takes the light to go from, say, the bottom to the top is longer here than it is from the bottom to the top here. And therefore, it's longer to go from the bottom to the top, back down to the bottom, one complete cycle of the clock. That time interval is longer for the moving clock than it is when the clock is at rest. Now we're going to call delta t0 the time interval for the light beam to go from bottom to top when the clock is at rest, and delta t to be the time it takes for the light to go from the bottom of the clock to the top and back down to the bottom when the clock is in motion. And we find mathematically when we go through the algebra and geometry that the relationship is delta t0 is the time when the clock is at rest, delta t is the corresponding time when the clock is moving. The square root here is 1 minus v squared over c squared. V is the speed of the moving clock, and c is the speed of light, 3 times 10 to the 8th meters per second. We notice that the denominator is a number that's always going to be equal to or less than 1, and therefore delta t will be a number that's always equal to or greater than delta t0, consistent with our thought experiment that moving clocks tick more slowly than do clocks at rest. Now the other thing we want to note on this is that it doesn't really matter whether I have a clock of this type consisting of a light beam going up and down and a moving clock that's identical with a light beam going up and down, or whether I have other types of clocks. Because all clocks that are within this same frame of reference, I can imagine that I have watches and pendulums and all kinds of different timing processes going on, they're all going to stay synchronized with this light beam clock. Similarly, when this clock moves along, all processes that move along with it are going to stay synchronized with it. The laws of physics are the same in any relatively moving reference frame as long as that reference frame is not accelerating. So within this entire reference frame, all clocks moving along are going to stay synchronized. We just use the light clock as a gimmick to get a handle on what happens with the timing of all clocks. So it turns out that since the light clock ticks more slowly compared to the stationary clock, all clocks moving along with that light clock will also tick more slowly compared to all clocks that are at rest with the stationary clock. Therefore, we can conclude that moving clocks tick more slowly than do stationary clocks. In conclusion, you may wonder whether or not this thought experiment actually works out when we do the real experiments. And it turns out that many experiments have been done, and in each case it's been experimentally verified that moving clocks run slower than those same clocks do when they're at rest.